Okay, good morning everyone. So today we'll see another important topic in analog circuits like power amplifiers. Okay, so this power amplifiers is also called large signal amplifiers. Okay, so till now we have discussed about only small signal amplifiers. So all the amplifiers we have discussed so far, those are called small signal amplifiers because in that small signal amplifiers we have to give the small signal range. The signal strength will be in the range of millivolts only, 10 millivolts, 20 millivolts, like that. Okay. So if the input signal strength is very less in the range of millivolts, so those amplifiers are called small signal amplifiers. Now, large signal amplifiers means we have to increase the signal strength. We have use this large signal in the range of 1 volt, 2 volts, like this. So those amplifiers are called large signal amplifiers, and other name is power amplifiers. Okay, so mainly these power amplifiers used to deliver the maximum amount of power to the load. Okay, that is the main aim of these power amplifiers. Okay, now actually these amplifiers are classified based on the operating point, especially. Okay, we have operating point or Q point, and the name is quiescent point, and the coordinates of this Q point is VCE, comma IC. Right, that means output voltage and output current. So from these quiescent values, we can find out the Q point. Okay, so based upon these Q point position, these amplifiers are classified as four types. These power amplifiers. Okay, one is class A amplifier, another one is class B, class C, class AB. So these are the main amplifiers: class A, class B, class C, and class A. These are the four types of power amplifiers. Of course, we have some more amplifiers also, but these amplifiers are based upon the Q point. And the remaining power amplifiers we have class D, class S, like this. So these are the major power amplifiers. Now, in this unit, we will discuss about these power amplifiers and the operation and equations, analysis, and derivation of the efficiency, especially, and the types of distortions, and especially harmonic distortion is very important in power amplifiers. Okay, and heat sink. Okay, let's see. First, introduction. See, when the output to be delivered is large, much greater than a milliwatts range, and is of the order of a few watts or more watts, conventional amplifiers cannot be used. Okay, that means the power is very large, output power is very large. Normal BJT transistors are not useful. So such electronic circuits delivering significant power to the load are termed as power amplifiers. Okay, for such cases we have to change the transistor type also. Okay, since the input to this type of amplitude is very large, at the time the loss in amplifier. So already I have explained. So for this power amplifiers, the input of this amplifier circuit is large. That's why these amplifiers are called large signal amplifiers. Okay. Now, in order to improve the circuit efficiency, that means efficiency means the ratio of output power to input power. That is called efficiency formula. Right? In order to improve the input efficiency, the device is operating varying conduction angles like 360 degrees, 180 degrees, okay, less than 180 degrees, like this. So based upon these variation in the conduction angles, the power amplifiers are classified as A, B, C, A, B, D, and S. So these are the various types of power amplifiers. Okay. Now, what is power amplifier? So the large signal amplifiers are used to obtain appreciable power from the amplifiers. Okay. That means if the input signal is large in amplitude or magnitude, the operating point is driven over a considerable portion of the output gas of the transistor. That means actually what is our intention? Our intention is we have to maintain the operating point in active region. Okay, we have different regions: active region, saturation region, cutoff region. Okay, so almost in all the amplifier circuits, the circuits are connected in active region. You already know that point. Okay, okay. So why we are making the operating point in active region means to work as an amplifier circuit. You have to act the transistor, you have to behave this transistor as an amplifier to connect this circuit in the active region. That means for the active region, what is the condition? Input junction is forward bias and output junction is reverse bias. That is the condition for activity. Suppose you have another region, cutoff region, saturation. So for saturation region, conditions are both junctions must be in forward bias. So in that region, the transistor acts as a on switch. Okay, similarly, in cutoff region, condition for cutoff is both junctions must be in reverse bias. So in that region, transistor acts as a open switch. So now no need to go in detail about this cutoff and saturation. Let's see about that. Now in the class A, sorry, first we will discuss about class A. So first class A, class B, class C, and class A. These are the four power amplifiers. Okay. So class A means if the Q point is placed near the center of the linear region of dynamic curve. That is class A population. Okay. That means the Q point position is center of the DC load. Like that is the Q point position, and the conduction angle is 360 degrees in class A. So the distortion is low for small signals, and conversion efficiency is also low. Okay, so in class A, the 2 points are important points are conduction angle is 360 degrees. That means you will get the output for full sine wave. Okay, that means the Q point is located at the center of the load line. Okay, that is class A. Next, what is class B? So in class B, the conduction angle is 180 degrees, and output this Q point is near the cutoff region. These are the 2 points. Okay, the conduction angle is 180 degrees. That means you will get the only half of the cycle only. For full sine wave input, you will get the output only half cycle. That is class B. Next, what is class C? So class C means that the Q point is located below the cutoff region, and the conduction angle is less than 180 degrees. Okay, less than 180 degrees. That is the that means less than half of the cycle simply in class C. Okay, so here the conversion efficiency can theoretically reach 100%. The stock is very high. These are using radio frequency circuits where resonant frequency may be used to filter the output waveform. So it, in class C, the conversion efficiency should be approximately 100% theoretically, but practically it is not possible. We may get around 90 like this. And applications of these class C radio frequency circuits. So those the resonant frequency may be used for filter the output waves. Mhm. And similarly, Class A, Class B are used in the audio frequency range, but Class B, Class C are used in the radio frequency range. The conversion change is important. That is another thing. Okay, so among these amplifiers, only Class A and Class B are used in audio frequency range. Okay, and remaining Class B and Class C are used in radio frequency range. Okay? Next, so this is the Class A concept. Class A. This is the Class A circuit diagram. Okay. So I already explained what is Class A, what is Class A definition. Just you please go through these points for 2 minutes. If you have any doubts, ask me. This is a Class A operation. Okay, so over. So here the class A is the most common and simple form of the circuit, and it is so the transistor is always placed to bias on so that it conducts during one complete cycle of the input signal waveform. Okay, see this figure. So this is a circuit, and here we are giving the input signal. This is coupling capacitor, input coupling capacitor, and there here we can measure the output signal. See there is a phase shifter, 180 degrees phase shift. Okay, simply it is a CE amplifier. So in CE amplifier, obviously we will get the phase shift of 180 degrees. Okay, and these two are R1 and R2 are the biasing resistors to provide required biasing, and RL this is output resistor or load resistor. Okay, so already you have studied the operation of this circuit. Now, so this is the simplest type of class A power amplifier. This single inlet transistor and output stage with the resistor load connected directly to the collector terminal. So when the transistor switches on, it sinks the output current through the collector, resulting in an negative voltage drop of the emitter resistance, thereby limiting the negative output cap. Okay, so here the efficiency of the circuit is very low, approximately 25 to 30%, and delivers small amount of output power for a large drain the power supply. Okay, like see this. This is all about the some theory about this circuit. Next we see the Darlington transistor. See, already I have explained this concept in previous classes. Okay, Darlington means common collector, common collector. So both circuits are CCCC. Mainly this Darlington circuit is used to improve the input impedance. Okay. The overall current gain Darlington is product of the two individual gains of the transistors multiplied together, and very high beta value along with high collector currents are possible compared to a single transistor circuit. Okay. To improve the full power efficiency of the class A, it is possible to design the circuit with a transformer connected directly in the collector circuit to form a circuit called transformer coupled amplifier. Okay. The transformer improves the efficiency. Yeah, absolutely. The transformer, if you use the transformer, maybe the transformer will be used to for power amplifiers to impedance matching. That is one of the important criteria. Okay. See, the third point, you see that line. The transformer improves the efficiency of the amplifier by matching the impedance of the load with that of the amplifier in the trans ratio. Okay. So one of the major important point is improving whenever there is an impedance matching happens, obviously we will get some maximum power, maximum output power, get the output side. Okay. Now this is the transformer coupled amplifier. See in this figure you have added one transformer at the output side between collector and loud, loudspeaker. Okay. So this is transformer coupled amplifier. As a collector current is IC is reduced below the quiescent point set up by the base bias voltage due to variations in the base current, a magnetic flux in the transformer core collapses, causing an induced EMF in the transformer primary windings. This causes an instantaneous current, instantaneous collector voltage. And these are some important equations. Please, all of you note down these equations. Okay, over. Right. PCE equation, ICE current, AC power, DC power, and this is the efficiency. Okay, this is efficiency formula: AC power by DC power. Okay, and this is all about the some important points about class A. Next, we will see about the class B. Okay. Actually, in class A, we have basically two types. One is series fed amplifier transformer. That's why we discussed. This is the second type actually. This is the class A transformer coupled amplifier, and this is the series fed amplifier, directly coupled amplifier. These are the two types. Okay. So when come, of course, in both amplifiers, we will get the approximate same efficiency, but there is some maximum amount of power with the transformer. We can use the transformer for impedance matching. There we will get some better efficiency than previous one. Okay, so this is directly coupled, and this is the transformer coupled. These are the two types. Okay, next we will discuss about the class B. So in class B also we have two types. One is push-pull amplifier, another one is complementary symmetry amplifier. So mainly the difference between these two is in push-pull we will use both same type of transistors. Okay. In class B, definitely in both configurations we are using two number of transistors. Number of transistors are two, but in push pull you use same type. In complement symmetry, opposite. One is NPN, another one is PNP. That is the difference between push pull and complement. And this class B is provides some about better efficiency than class A. Okay, and approximately 78.5 like this. Okay, now flag amplifier balances center tap transformer. This is a center tap transformer. It splits the incoming waveform signal into two equal halves. Here, we are using the center tap transformer. It divides the total input signal into two equal parts to two number of transistors, and it's 180 degrees out of it. And these two, see this figure. So in this figure, this is the input signal from the source, and this input signal is divided into two equal parts, but both are equal in magnitudes but out of phase. I mean opposite in polarity. And this signal will be applied to first transistor base. This signal will be applied to second transistor base. So based upon these signal polarities, the transistor operation follows. Okay. So when the transistor one, when the Q1, the Q transistor Q1 conducts for a positive half cycle, okay, and this conducts for negative half cycle. Okay. So this finally you will get the output, no problem, the operation. And see this theory. So the approximately percentage is 70%. So theoretically it is 78.5, but practically you will get around 60 up to maximum up to 70%. Okay. Okay. So please read these points. This is the operation actually. Please go through these points. Okay. No, class B. This is the output characteristics. See, this is the output characteristics figure. And x-axis I have taken the output voltage VC, y-axis I have taken output current IC, and this is called DC low line. Okay, and this is output voltage, and this is output signal. Actually, we are output signal. This is output voltage. See, in class B, so in actual operation as per theory, in class B, we get the half cycle only as output. Okay, see, this is the input signal. This is the input signal full sine wave, and the output side will get only half cycle based upon the transistor operation. The class B amplifier has a big advantage of class A, that there is no current flows through the transistor when they are in their quiescent state. That means with no input signal. Therefore, no power is dissipated in the output transistors or transformer when there is no signal present, unlike class A amplifier. This is the advantage of class B. But so the overall conversion efficiency is greater than the equivalent class A. The efficiency is high 70%. So maximum we will get 70% of efficiency. So with this class B. Okay, this is class B push pull. Okay, in class B push pull. So what we have learned in class B, we are using two transistors in same type. Okay. Next we will discuss about complementary symmetry. Complementary symmetry. So complementary symmetry means here we use two different transistors. One is NPN transistor, another one is PNP transistor. So one of the main disadvantage of class B amplifiers, which is balanced center transfer design, making it expensive to construct. So that is a disadvantage. In both the amplifiers, we have to use a transformer. That transformer should be the balanced center transformer. It is costly and bulky. That is one of the disadvantage in class B. But in complementary symmetry, that does not use of any transformer. Yeah, this is the advantage of complementary symmetry. In class B push pull, we have used transformer, but here there is no need of transformer. This is the figure. Complementary C. Here we are using one NPN transistor, one PNP transistor. But even though based upon the operation, we will get the full sine wave at the output side. But in class B push pull, what we have learned in class B push pull, we are using two same type of transistor along with the center tap transformer. That is the drawback. The center tap transformer is one of the drawback. But in class B complementary symmetry, there is no need of transformer. Okay, even though you will get the full sine wave with the help of two different transistors, one NPN, one PNP. Okay, see, this is the input signal. So what will be the operation? Tell me. The input signal, the same input signal is transmitted to two transistors bases based upon operation. For the positive half cycle, here you will get only positive. The transistor contains only for positive half cycle, so that you will get the only positive sine wave, positive cycle. For the negative cycle, this transistor will be condensed, so you will get the output. By combining these two signals at the output side, I mean across the load, you will get full sine wave. Simple, very simple operation. And these are all the four registers are biasing registers to provide this required biasing. Okay. Okay. Hmm. Okay. Read this theory. So whatever I have explained the operation, the same points will be replicated here. So go to these points for a few seconds. Just see the figure and parallelly you read these points. Okay, over. Now, next one is class AB. Okay, the base emitter voltage to be greater than 0.7 for silicon bipolar transistor to start conducting. We have replaced the two voltage bias resistors connected the base emitter transistor with two silicon diodes. So it will become the class AB. See this figure. The difference between class AB figure and class C, these are the difference. See here in this figure, we have used two resistors RB1, RB2 in place of two resistors. Here we are using two diodes. That is the difference, and the entire figure is same. Okay, very simple. The only difference is we are replacing the resistors with the two diodes simply, and the remaining figure is same and operation also same. Here the main problem is this is the point. The base emitter voltage, to maintain this voltage, base emitter voltage, we have added two diodes. The circuit is compromised between class A and class B configuration. The very small diode biasing voltage causes both transistors to slightly conduct even no input signal is present. That is the important point here. An input signal waveform will cause the transistor to operate a normal in the active region, thereby eliminating any crossover distortion to the push. Okay, so in class B you have a chance of push-pull, I mean crossover distortion. So how to avoid this crossover distortion is by using this class AB. Okay, see, forward draw. These diodes are biasing diodes, and these two diodes are special diodes are called biasing diodes or compounding diodes. Match the capacitor matching transistor. Okay, right. See some important points about these three amplifiers: class A, B, and next we will see the class C. Okay. Class B amplifiers greatly preferred over Class A designs of high power applications such as audio power amplifiers and public address system. So, like the Class A amplifier circuits, one way to greatly boost the current gain of Class B is to use Darlington. I already have explained Darlington also. So, in Darlington, you will get the maximum current gain, high current gain. That is the advantage of Darlington. Okay. Class C. So, let's see the. This is Class C power amplifier. Input signal. This is a biasing resistor, the transistor, and this is the tuned circuit or LC circuit. Okay, now let's get into this topic. So, Class C amplifier is a type of amplifier where the active element conduct for less than one of cycle. That means the conduction angle is less than 180 degrees. Okay, so less than half cycle means the conduction angle is less than 180, and its typical value is 80 to 120. So, approximately 80 degrees to 120 degrees. The reduced conduction angle improves the efficiency to a great extent, but causes a lot of distortion. Okay, so whenever the conduction angle is decreased, the efficiency will be more, but there is a chance of distortion, high distortion. Due to the huge amount of distortion, the classic are not used in audio applications, so that is the drawback. So in class C, distortion will be high. Okay, at the same time, efficiency also high, distortion also high. So with this, we can't use this class C in audio application. The most common application class A are radio frequency circuits, RF oscillator, RF amplifier, etc., where there are additional tube circuits for retrieving the original input signal from the pulsed output of the class. Okay. Okay. So the distortion caused by the amplifier has little effect on the final output. And input and output waveforms are typical class C amplifiers are shown in figure. Yeah, let's see this figure. This is the input signal, this is the output signal of class C, and these are the output characteristics. See, this is the input signal, but the output signal is now less than half cycle. Okay, this is the figure, and this is the operation. Now, see this figure and go to these points. And these are advantages: high efficiency, excellent in radio frequency applications where physical size are a given power output, and disadvantages applications. So note down these points. All of you note down these points. Applications, disadvantages, and also advantages. Okay. So next one, power and temperature. The maximum power rating of the transistor is largely governed by the temperature of the collector. And as can seen from the power derating graph, this power dissipated. This junction gets too hot and the transistor will be destroyed. So typical maximum temperature is between 100 to 150. Suppose if the temperature is very very high, there is a chance of damaging the transistor. So we have to maintain proper temperature. Okay, so some devices can withstand higher maximum junction temperature. The maximum power output available from power transistor is closely linked to temperature, and about 25 degrees falls in a linear manner to zero power output. The maximum control temperature is reached. Okay, so temperature also one of the important parameter in these components. Okay, so we have to maintain proper temperature. See this power dissipation versus maximum temperature. This is the graph. Okay, so initially up to 25 degrees centigrade, this is safe. The safe is constant. When the temperature increases, the power dissipation decreases like this. This is the graph, and these are some power transistors. Okay, I mean, sorry, heat sinks. This is heat sink. So it's using a class by unit. By ensuring that heat produced transistor can be removed by exchanging the transfer surrounding a quick pause method, two is about highlights of the relation between power transistor and the heat sinks. These are heat sink. A device attached to transistor for the purpose of removing heat. The heat sink is mainly used to absorb the heat. Okay, the physical concept of power transfer is therefore designed to maximize the transfer of the heat to the heat sink. Okay, so the purpose of transfer is transfer the power to heat sink in addition to a usual collector layout, right? A collector of a power transistor which has a much larger area than the small signal transistor. So these are the images. Okay, next. How to calculate this thermal resistance RTH? See, this is the theory and the figure. MOSFET, comparator, MOSFET power switching module, and low pass filter. So what is this comparator? For this comparator, we can give two inputs. One is audio sine wave, another one is high frequency triangular wave. These are the two inputs for comparator, and this comparator compares those signals and generates the output waveform like this high frequency PW waveform. And this is the input to this circuit. And the output circuit is the inductor. This is the output of this MOSFET. Then we are using a low pass filter. That means it allows only Only low frequencies blocks high frequencies to the loudspeaker. Okay, so see this theory and figure. Okay, now next class C classes, and these are some other power amplifiers. Class G, class H. Okay, it's not much important, but just for idea. Okay. Okay. Next, very important thing: crossover distortion. Okay. It produces zero voltage, flat spot, or dead band and the output voltage shape as it crosses over from one half the waveform to the other. The reason for this that there is transition period when the transitions are switching over from one to the another does not stop or start exactly zero crossover point. There is small delay between the first transistor turning off, the second transistor turning on. That means when in class B, especially in class B amplifier, we will get this type of distortion. We will have this type of distortion because in class B we are using two transistors. Both are same type. The first transistor is off, and then the second transistor will be on. So meanwhile, in this gap, there is a gap between the both transistors will be in off condition. Okay, so such cases we will get this type of distortion. See this point here. Do not stop us right cause causing small delay between the first transistor turning off and second turning on. This delay results in both the transistors being switched off at the same instant in time, producing output wave shape. See, so this is the transistor 1 on, this is the transistor 2 on. When the transistor off, before conducting the second transaction, there is a small time gap. There we will get this GC, zero output. This is called crossover distortion. So in order there should be no distortion output waveform, you must assume that each transaction conducting when its base emitter voltage rises just above zero. But we know that this is not true because for silicon paper lens, the base voltage is 0.7 volts. Yeah. For ideal case, it is okay. It is possible. For ideal transistor, the cutting voltage is 0 volts. But practically, it is not possible. For silicon, the conducting voltage is 0.7 volts. Okay. Only if the input voltage reaches to 0.7 volts, then only it starts conducting. So before 0.7 volts, it will be an off condition. So definitely, there is a crossover distortion class B. So to avoid this, we can use the class AB mode. Already I explained this class AB mode. Okay. And these are the characteristics. This is the input cycle, input signal. These are the characteristics, and this is the output waveform in class B. So crossover distortion is very important. Okay, and these are the push-pull amplifier pre-biasing circuits. Some other circuits pre-biasing problems are going to be reduced density applying a slight forward bias variable. Okay, to the base of the two by a center type transformer. Thus, the transistor are no longer biased at zero cutoff point instead of pre-biased. Okay, the push-pull amplifier with pre-biasing. This is the so second pre-biasing with the diodes. Just we are replacing these resistors with the diodes. Okay, the pre-biasing voltage is for a transformer less amplifier. Moving back to point was the critical position cutoff point, thus allowing each transistor to operate with active region slightly more than half or 180 degrees. In other words, 180 degrees plus bias. The amount of diode biasing voltage present to the base terminal of the transistor can be increased in multiples by adding additional diodes in series. This then produce amplifiers on class AB, already I class AB mode. So okay, in class B generally we are using these two resistors. In place of these two resistors, diodes. This is the class A. And these are the class AB output characteristics. Okay. Then to summarize the crossover distortion, what happens if we have to take bias is cutoff point. This results in both transistors being switched off same instant time wave from cross zero. By applying a small bias voltage by using a resistor to deliver circuit or diode biasing, this crossover distance can be greatly reduced or even eliminated completely by bringing the transistor to point switched on. So this is the solution. So how to open this crossover distance? These are the points. Okay. And next application of biasing voltage producers. That is a class AB by using some biasing voltage. Then the difference between push class B and input class AB is the biasing level applied to the output transistors. Okay, and see this all the theory very important points. Okay, let's go through these points. Okay, okay. So this is about the power amplifiers. So till now, what we have discussed so far, four types of power amplifiers: class A, class B, class C, class AB. So what is the difference between four amplifiers? So in class A, the convection angle is full cycle, that is 360 degrees, and position of the Q point is center of the DC low line. Okay. And what is class B? In class B, the convection angle is half cycle only, that is 180 degrees, and the position of the Q point is mm, below the center of the low line. Okay. Next, class C. Okay, less than half cycle. And similarly, class AB, more than half cycle, less than sorry, more than half cycle, less than full cycle. And there we have seen the operation of each and every power amplifiers. Okay. In class A, we have two types: series fed to directly coupled. Similarly, class B, we have two types: push pull amplifier and complementary symmetry. In class C amplifier, then class AB. Okay. In class B, we got the crossover distortion. Okay. So to avoid those crossover distortion, we go for class AB mode, in which we are using two diodes, special diodes, instead of the two resistors. Okay. And then to reduce the heat, we can use the heat sink. Okay, some power transistor, heat sink, etc. Okay, so that is about this power amplifiers concept. So another name of this power amplifiers is large signal amplifiers. Okay, okay, is everything clear? Okay, so please all of you go through this PDF for reference. Okay, if you have any doubts, so please ask me in the next class. Okay, students. Okay, all of you, take care. Thank you. Bye. Bye, all of you.